problem has a solution if you can somehow have inverse of delta d. So if we can have inverse of delta d, okay, then what's going to happen? I'm going to have a solution, which is a solution operator actually, the inverse of this operator, which is going to take as an input f, okay, and give me the solution as an output actually. Okay. So we would like to do something similar here actually. Alright. So what we do about delta d, so we want the invertibility of this whole actually. Okay? This whole operator. Okay? But there is something interesting. We know, just think about it. Isn't that the same kind of a situation? Instead of delta d, you have this whole operator operated onto you, giving you f actually. So if you can somehow invert this, you can have a solution. In other words, under what conditions you can invert this operator? That's what would be the key question to answer. Now about delta d, I already know that it's bijective and bounded actually. So delta d is not a problem. Okay? The real trouble is this operator.
Not the bounded.
The real trouble is this operator. Okay? Hence this operator. Hence invertibility. So you can say the problem or the solution of the problem, existence of solution of problem
depends on the existence of inverse.
Problem depends on invertibility. Okay? So invertibility of what?
I
minus t.
I minus t delta d inverse. So delta d inverse is a map from L2 to H2, and t is again sending from H2 to L2. So this guy is a map from, so it's like a linear operator at least, from L2 to H2. Okay? And when you subtract I from it, okay, you still, you're going to have an operator from L2 to L2. So this is an operator from L2AB
to it.
and to L2AB. There's nothing, too much trouble making it. Alright? Now the question is that under what condition this operator is invertible?
Continuous. Continuous linear and bounded.
No, I mean, just think about it. We just did a lemma actually, the Newman series. What does the Newman series is telling me? This.
Operators.
So this is telling me that I minus A is invertible. So A is basically this operator, TD inverse, is invertible if which conditions are satisfied?
Norm, series of norm power of norm powers.
This is infinity is satisfied. Is finite if, okay, this is finite actually. Now what should I impose conditions, okay, on this so that I can make sure that the series formed by, in other words, n equal to 0 to infinity, this t delta d inverse is finite actually. So what conditions shall I assume? In other words, that's a series of numbers, okay? And I want this series of numbers to converge actually.
0 and 2.
So what is a trivial way to, I mean, okay, if this is 0, then what we are talking about, we're not talking about anything trivial actually. So what I'm saying is that under what conditions this thing can converge actually. Okay. The one of the condition could be that, just think about it, if I assume this guy to be less than 1 actually, or I assume that this guy to be a contraction, because this is what a contraction means. Okay, what's a contraction map? Okay, the norm of it is strictly less than 1. So if somehow I assume, so that's one way to deal with it. There can be other ways as well actually, but one potential way to deal with it is that you assume that this T delta D inverse has a norm which is strictly smaller than 1 actually. So if this would be the case, this must converge. And if this converge, the inverse exists. And if inverse exists, problem has a solution actually. Are you getting the point? So in other words, that's one of the sufficient conditions.
Sir, even if it is less than 1, let's say it's 0.5. So adding that 0.5 infinite times.
So in other words, you have to choose something less than 1 cleverly in such a way that the series converges. Okay, so okay, I'm not saying that take any random value. Okay, so you have to obviously choose.
Power, like A is power n, so T delta D inverse, shouldn't it have power?
What do you mean by?
In
A के ऊपर n लेना है तो
Ah, okay.
फिर 1 over
So you are saying that shouldn't this must have a power n actually? Yes.
now 1 over 2.
Yes. Okay. Is it making sense? So if we have this, our life is much more easy. Okay. Any number smaller than 1 would work actually. So that's what you call
Geometric series.
Can I be more explicit about it actually? What is the meaning of this actually?
So now sir, this is simple geometric series.
No.
Power n hai.
No. Okay, it's a geometric series, but
Why would it?
what does this inequality mean actually? Okay, I would say that this actually means that
Noun is
there exists.
bounded
If there is a Q, okay, in the interval 0 and 1, it's like a 0 to 1, such that the norm of TU, L2 norm of TU can be estimated by Q times norm of TU. So this can be even made more precise actually. So if this condition is satisfied, this is satisfied, and hence the series converges. And if the series converges, operator is invertible and you have a solution of your problem. Okay? Maybe it would be a good exercise to think that what is the relationship between these two estimates. Okay? Anyway, is it making sense? So what we did in this discussion, that we somehow used our lemma regarding the Newman series, and we found a sufficient condition for the existence of the perturbed Poisson equation actually. A sufficient condition.
Sir, we have inverted just I minus t and multiplied by this inverse.
I mean, delta d is already invertible actually. So you just compose their inverses and you can get the inverse of what you want. Okay? Delta d is already invertible. Okay?
Yes, sir.
Well, so that's one example. I would like to do another example, and the last example of this chapter, which we have in front finish up this chapter. And I would like to discuss that, there is a type of integral equations which is called a Volterra type integral equations. And I'm going to use these two lemmas to show that the Volterra type integral equations, under certain conditions, you have a solution. Volterra is the name. Okay. So what's a Volterra type integral equation? So what's an integral equation in the first place actually? So we know the differential equations. So what's a differential equation? It's like a differential equation, so an equation roughly in which, so it's like a function of, functions, function of u and its derivative, is equal to 0. That would be equal to 0 would be a generic form of differential equation. But essentially, what we say that, okay, if the unknown quantities appears in, on the derivative sign, you say that, okay, that's a differential equation. But now, if the unknown things appear under the integral sign, actually, you're going to call them integral equation, and then you have a whole theory of integral equations. I'm not going to discuss it. I'm just going to take one particular abstract kind of Volterra type integral equation, and I'm going to show that for each such equation, under certain assumptions, you can always have a unique solution. Okay? So that would be another application of Newman series. So let M be an operator. Yeah, it's a function actually. A cross B into the A cross B into the the field K. Okay. Be a continuous function. Okay. Then following is called Volterra integral equations. Okay, so like a Volterra type integral equation. So what is the Volterra type integral equation? So I'm interested in u. So this looks like this. So u of t minus the integral from a to some t, where t is some instant in the interval a to b. Okay. M of ts times u of s ds equal to f of t. So kind of f is known to me, m is known to me, and the question is, what is u? So there are lots of techniques, as you have techniques to solve differential equations, you have also lots of techniques to solve such integral equations. So I'm not going to talk about those techniques, I'm going to talk about that such an equation has a solution, a unique solution always. Okay? For given f in the space of continuous functions over the open interval. So what do you think? What should I do cleverly so that this equation can look like the abstract equation that we have actually?
So let's do modify integral operator.
Modify current operator.
I mean
Why do
a,
we modify?
a times u.
So why we shouldn't treat this whole as a times u actually?
Of course.
So in other words, let's treat this integral as an integral operator actually. Okay? consider an operator V. Let's give it a name, V. Okay. From CAB enter CAB and define V, that when V is operated onto some U, which is where the U is in CAB, okay, and everything operated onto T, then it's going to give me an integral from A to T, okay, M Ts, which is the kernel actually of this integral transformation, okay, times U of S and T of S. Making sense? Okay. So now I can modify my problem. So now my equation, maybe I can call it double star, takes a form, and that form would be
U minus VU.
So it's going to be U of T minus V
U of T.
U of T equal to f of T. Okay? And in other words, I am interested in, so it's like that's how my abstract equation now looks like actually. So if I want to solve this abstract problem, what I need to do,
Inverse of I minus.
I need to make sure that the inverse of I minus V exists. And when the inverse of I minus V will exist,
V power n.
if the series of formed by the powers of V and their operator norms, okay,
It's fine.
inverse is actually. So in other words, the sufficient condition is satisfied. So if that is satisfied, we are almost like done actually. That's a little lemma. Okay, so here's a key thing, one thing that we are missing. In what space we are looking for the solution of this problem? In CAB. So everything is in now the space of continuous functions over the interval A to B. Okay? So here's the lemma. What we can show is that with all this notation M and V and so on and so forth, we can show that V raised to n, when operated on the f of t, can be estimated by m raised to n and its infinity norm times t minus a n over n factorial times the infinity norm of f for all f in CAB, and as a consequence, let's show that the norm of V n can be written as can be less than or equal to norm of f raised to n infinity t minus a raised to n over t minus a, say b minus a, t minus a is smaller than b minus a, okay, over n factorial. So if this is true, this is easy actually. So it's not a big deal to deduce this inequality. Okay. So this norm is what? This norm is L from C into C actually. So CAB into CAB. Okay, so that's operator. How can I show it? Show it inductively. The first thing is that you want to prove this key inequality, show it inductively. Okay, pretty good exercise. But at least for one power it's pretty much simple that if you take T and ds and u of s ds, okay, f of s, f of s ds, then you can get what? Less than or equal to what? So take a supremum here and take a supremum here, you know. So I can take a supremum over what? Over, okay, so first I can take a supremum of over s here and supremum here actually on s, okay, and what? Try to figure out for this. It's not that difficult. Just think about it. Just see these two terms. Does it telling you anything? Something to do. Okay? So you have to cleverly play with the supremum. Okay. And then you need to repeatedly apply,
Sir,
V's actually.
A to T है तो A to B भी बड़ा हो जाएगा फिर तो A to B.
Anyway, try to write a precise proof of it actually. So assume that, I'm assuming that this lemma is true, okay? This lemma is something for you to do actually. Now if this lemma is true and this inequality is true, then that's what is making my life easier actually. Just think about it. Because I just need to do what now? N equal to 0 to infinity, e raised to n, and its operator norm. Okay? So will be equal to, or maybe less than or equal to, n equal to 0 to infinity. Okay? And its infinity norm, b minus a raised to n over n factorial. Okay? And what? Do you have a guess for this thing actually? What does it look like?
Norm of n power n.
Norm of?
Infinity norm of n power n.
Okay, m power n actually, sorry. Yes, there must be. Then this is nothing but e raised to infinity norm, okay, times b minus a. Agree?
E power x.
So that's e power, that's a series of e power x actually. And just take x this up. Okay. Now is this guy finite? Is this guy finite?
Yes.
G sir, continuous sir.
So that's fine. So if this is finite, so this series is finite. And if the series is finite, I minus v is invertible. And if it is invertible, there exists a unique u.
And CAB.
There exists a unique u such that it solves
Volterra Integral equation.
Volterra Volterra integral equation, Volterra type integral. Simple. So you see, these results are powerful. They kind of give you at a very basic level some sufficient condition in order to make sense of things. Okay? So I hope. So what we did essentially in this chapter, we took this operator theory to a new level, and we kind of considered some of abstract problems, okay, and we considered and understood, tried to understand at least, okay, some of the sufficient conditions for the existence of unique solution, existence and uniqueness of the solution for abstract problems actually, okay, and we applied those to some of concrete situations actually, okay. What we are going to do next, so I'm going to jump now. So we want to have a break of maybe 2-3 minutes. How much time do we have?